Welcome one and all to this video, an introduction to integration on curved Riemannian and semi-Riemannian manifolds using the pullback of volume forms. Okay, so integration on curved manifolds is a cornerstone of differential geometry, generalizing classical integration from Euclidean space to manifolds. On Riemannian or semi-Riemannian manifolds, the volume form plays a central role, encapsulating the geometry induced by the metric. Now, the pullback operation provides a way to simplify integration by transferring the problem to a Euclidean domain. Okay, sounds like a bit, but you'll see how it all works out. Okay, so Riemannian manifold, this pair here, M the manifold and G a metric, defined on the manifold, is a smooth manifold equipped with a positive definite metric tensor G, which defines an inner product on the tangent space to the manifold at the point P, at each point P, TPM, and that is the contraction of two vectors, the inner product of two vectors under the metric G, under the given metric, is positive, greater than 0, for every non-zero vector V. Now, in Euclidean space, the metric is just the matrix whose diagonals elements are just 1, diagonal entries are 1 and everything else is 0, so it doesn't play an obvious explicit part, and so the contraction of the two vectors, a vector with itself, a non-zero vector with itself, is just the familiar inner or dot product or scalar product. And so for a Riemannian manifold, this is positive, greater than 0. A semi-Riemannian manifold relaxes this by allowing G to have a mixed signature, as in the case of space-time in general relativity. So in special relativity, you've got the diagonal has -1, 1, 1, 1, four-dimensional space-time, or in some the other convention is to have +1 in the time component and all the others negative. So there's two conventions, so you need to check which one you're working with. In general relativity, same thing. We have -1 in the leading entry and 1, 1 and non-zeros all down the diagonal. All right, so the volume form, the metric tensor G determines a natural n form on an n-dimensional manifold M, if M is orientable, known as the volume form. So for a Riemannian manifold and semi-Riemannian manifold, the volume form under the metric G here, and that has to be written there because its volume form will depend very much on the metric. All right, so this is the square root of the absolute value of the determinant of the metric, and then multiplied by the wedge product of the basis 1 forms up to the degree of the manifold. In this case, an n-dimensional manifold, so there's n basis 1 forms wedged together. Okay, in the Euclidean case, the determinant of G is just 1 because it's the identity matrix, and the determinant is just the multiplication of the 1s along the diagonal element, and so that just gives you the absolute value of 1, which is 1, and square root of 1 is 1, and so it doesn't explicitly appear. You would just, in the Euclidean case, have this dx1 wedge dx2 all the way up to dxn. But on curved manifolds, you must account for the metric term here. Okay. Now, another aspect on the manifold is it's generally the case that you don't have one coordinate system to cover the entire manifold. Generally, it does not happen. And so we're going to have a local coordinate system on M, a coordinate patch, a number of coordinate patches together form an atlas and cover the manifold. So in our case here, our local coordinate system S, x1, x2, xn, and determinant G is the determinant of the matrix representation of G in these coordinates. And so here's our manifold M and dimension n, and here's our local coordinate system here, which covers part of the manifold S, and it has coordinates x1, x2, xn. So the volume form is used to define integrals of scalar functions on M, and incorporates the curvature of the manifold through the square root of the absolute value of the determinant of G. I'll come to this bit about scalar functions shortly. Integrals of scalar functions is what I'm going to get at. All right, so integration on a Riemannian or semi-Riemannian manifold. So to integrate some scalar function f over m, over the manifold M, we use the following volume form. The integral over M, our manifold, is the scalar f, or maybe I should give it is F times the volume form here over M, and so that's equal to the integral over M of F times the square root of the absolute value of the determinant of G, and then the wedge product of the individual basis 1 forms up to N. So what might F be? Well, in general relativity, you might be looking, or special relativity, F might represent some sort of energy density, and you're going to integrate it over a part of space-time. So again, that coordinate system S I was talking about earlier, this one here, if M represents the whole of space-time, you might be interested in a local patch of space-time, and you would have a coordinate system for that local patch of space-time. All right, and so the integral of this, let's say F is the energy density or some other scalar of interest, is F times the volume form here. Okay, which if we write that, expand that a bit more, is F times the square root of the absolute value of the determinant of G, dx1, wedge, dx2, wedge, all the way up to dxn. Now this integral is coordinate independent and reflects the geometry of M. Pullback of volume forms, so it doesn't matter what local coordinates we use here, it has the same form. Pullback of volume forms, so let phi, we've got some map here, I'll talk about, show you a diagram how that fits in. So phi is a map from a set U contained in Rn in Euclidean space, because remember how we were going to take this integral here and transfer this whole problem through the pullback to a simply Euclidean space where we can use our general vector calculus to conduct the integral. That's the whole point of the whole video. Okay, so phi will be a map from some set U, I'll show you a diagram shortly, contained in Rn into S contained in M. Be a smooth parameterization of M over an open subset U of Euclidean space. So phi is a function of the coordinates U1 to UK in the set U, so open subset U of Euclidean space, and it's mapped into S contained in M, so it gives us the coordinate functions x1, a function of the first coordinate function, which is a function of U1 to UK, x2, which is a function of U1 to UK, up to xn, which is a function of U1 to UK. Now, the pullback, phi upper asterisk, volume of the volume form with the metric G, transforms the volume form on M to U, enabling computation of the integral in a simpler domain. And that's the whole point of this video. We're going to take this integral here on the Riemannian manifold M, and we're going to pull it back to a simpler Euclidean domain that allows us to perform the integral more easily. We'll see how that works across this video. All right, so here we go. Here is our manifold M again. Here is our local coordinate system on it, x1, x2, xn. Okay, here is our map, which takes us from Rn space, n degree Euclidean space, Rn, of coordinates U1, U2 up to UK. All right, this open set U, and it will map that to S under this map, which maps the open set U contained in Rn to S contained in M. All right, and notice this is the manifold M is degree N, and the subset here, the local coordinate system, is also of degree N, dimension N. So we're going to map this to here, all right, contained in Rn. And I should point out under this map here, I better point out that at the point P, you have a tangent space, which is not shown in this diagram, so as not to make the diagram too messy, but there's a tangent space at the point P in which the vectors at that point in this open set exist. There's a tangent space at the point 5P here in which the vectors at this point. This tangent space here, all the vectors are tangent to this point of the set S, of the submanifold S, all right, are to be found, but again, I'm not putting that here. What I will put in, though, are the cotangent or dual tangent spaces here, and the volume forms here are represented by the blue here. All right, so here's the volume form G on M, okay, the one I was talking about earlier. Remember, dx1, wedge dx2 all the way up to dxn, and all that multiplied by the square root of the absolute value of the determinant of g. That's on M. In our coordinate system S here, our local coordinate system S here anyway, it's defined. So here, the cotangent space of the point 5p is right here. If the tangent space was shown, it would be up here. I'll put them up here at the point P and the point 5p, but both the tangent space and the cotangent space are coincident with each other at the point 5p in this case and the point P in this case. But again, I'm not showing the tangent space here because I don't need to use them for this discussion. So the cotangent space here is T upper asterisk, T upper asterisk of U at the point P, and T upper asterisk, the cotangent space of the set S, or the submanifold S at the point 5P. All right. And then what happens is that we take the volume form here and we pull it back under the metric, the volume form under the metric G, and we pull it back from this cotangent space to this cotangent space, where the integration here will be easier for us to perform. Okay, so that's the situation. So phi is a map that takes points in the set U contained in Rn to the set S contained in M. This is dimension n and this is dimension n as well. And S is dimension n as well. All right, so the pullback definition. So the volume form under G is this object again on S. Then the pullback is phi asterisk fold G is this thing, the square root of the absolute value of the determinant of G, composed with our map phi. Okay, because remember this is a scalar here, and we want to compose it with phi as part of the pullback to the open set U. We need, because it's a coordinate transformation from the x coordinates to the u coordinates, we need the determinant of the Jacobian here. All right, so that must be included in the pullback. All right, another way of writing that is just this. Well, that's the same thing. The determinant of this object here, another way of representing the Jacobian. Then in terms of the new coordinate system, the u1, u2 to un on the open set U in Rn, in the Euclidean space. Remember, x are the coordinates on the Riemannian manifold M, or the local submanifold S within that, and U are the coordinates on the Euclidean space. Another way of writing that is, I'm just showing you the notation. There's just at least 3 different ways of doing it here. Remember, these are the coordinate functions phi I. Just to remind you of that, so where phi equals a function of the coordinates on U of U1 to UK, and the coordinate functions x1 of UI here just being an abbreviation for 1 to k, I is 1 to k here, up to xn, U again is a function of I is 1 to k. I wrote it that way just to save space. These are our coordinate functions phi I to phi n, right? So phi 1 will just be x1 of ui, phi n will be xn of ui. All right, now J subscript phi is the Jacobian matrix of phi with entries partial phi I, partial uj, up here, and the determinant of the Jacobian under this transformation, coordinate transformation, is the determinant of J subscript phi. All right, so integral transformation. So the integral of a scalar function f over m, putting it all together, can be written as the integral of our scalar function f times the volume form under G on m is now the integral on U, the Euclidean space, f composed of phi, because we're pulling f back to phi, so it's f composed of phi, square root of the absolute value of the determinant G in those coordinates composed then of phi. Okay, then the absolute value, notice this time the absolute value of the determinant of J phi. This is to keep the orientation consistent. We want this to be a positive volume element to perform the integral. When we're just doing the pullback, we didn't worry about the absolute value of the determinant here, but since we're going to integrate, then we need a positive volume element here. Okay, because signs with integrals matter. So example, how about integration on a curved space? Let's take our two-dimensional Riemannian manifold M to be the unit sphere S2 embedded in R3. Now the metric induced by the Euclidean metric in R3 is this one. G is 1, 0, 0 sine squared theta. In spherical coordinates theta phi, where theta is between 0 and pi, and phi is between 0 and up to 2 pi. Now the volume form, the determinant of G is det G. Well, the determinant of that is just sine squared theta. Right, that's the determinant. And then the volume form is the square root of the determinant, if you remember. So square root of sine squared theta, d theta wedge d phi, which is sine theta d theta wedge d phi. Now that's on M, okay? So the integral of a function, so to integrate a scalar function f, which let's take as a function of theta and phi, they're the coordinates we're working with on M, over S2. So the integral S2f the volume form under the metric G is then just this thing here, the integral f of theta phi sine theta d phi. All right. And theta from 0 to pi and d phi from 0 to 2 pi, from 0 to 2 pi. Now what we're going to do is pull it back to the Euclidean domains, back from the manifold M back to the open set U, so parameterize S2 with phi as a map from U contained in R2 to S contained in R3. Phi of with coordinates U, V, okay, on U. So that becomes sine U, cos V, sine U, sine V, cos U. Now here, we would express each point of S2 using sine theta and phi is equal and so on here, and that would give us our coordinates in R3, X, Y, Z for this unit sphere, or the surface of this unit sphere. And what we're going to do now is just do a quick coordinate change here. So it's a little bit of a simple problem. I'll do a more challenging one shortly, but we're going to go from theta phi to UV. Remember, theta phi on M to UV on U. All right. So U is E, and what we're going to do is it's just a simple problem at the moment. We're going to just swap the coordinates. U equals theta, V equals phi, as you can see here. So instead of sine U cos phi, instead of sine theta cos phi, and sine theta sine phi, and cos theta, we're just going to do the coordinate change where U equals theta, V equals phi. Very, very simple coordinate change. U is going to be from 0 to theta, V will be from 0 to 2 pi, just like it was for theta and phi. Okay, so it's really a simplified problem here. All right, well, the Jacobian in this case here is this, which is this matrix here of partial derivatives, d theta du. Well, since theta equals u, then partial theta with respect to partial u will just be 1. Partial theta with respect to v will be 0. Partial theta with respect to partial v, will be 0. Partial phi with respect to partial u is 0. And since v equals phi, partial phi with respect to v will just be 1. Well, the determinant of that will be 1. Okay, hence we have d theta equals du and d phi equals dv. So the pullback of volume G to U contained in R2 is the pullback of volume G is the square root of the absolute value determinant G composed with phi. Okay, so determinant of this du wedge dv and the new coordinates, that becomes just sine u du wedge dv. Okay, previously this would have been sine theta d theta wedge d phi. So the integral becomes integral over S2 of f under the volume form here. It's just f composed of phi of uv sine u du d phi. Okay, that's all it would have been, and then you would evaluate that, whatever f is, whatever it is. Okay, just move on again. So key points. So the role of the metric tensor. The metric tensor determines the volume form and accounts for the curvature of the manifold. And 2, the pullback simplifies computation. The pullback reduces the integration problem to a Euclidean domain where standard techniques apply. All right, and the coordinate independence. The integral of f under the volume form G over the volume form G, on M is independent of the choice of coordinates, reflecting its geometric nature because it doesn't matter what coordinates we use. What we're going to do now is pick another example just with a little bit more substantial coordinate change so that you can see the full part of it in operation. All right. So let's explore integration on a two-dimensional hyperbolic space, H2, which is a curved Riemannian manifold with constant negative curvature. Right, so the hyperbolic plane, H2. So the hyperbolic plane can be represented by the Poincare half-plane model. H2 is a set of order pairs xy that belong to R2 with the restriction that y is greater than 0. So with the Riemannian metric being g is 1 on y squared dx squared plus dy squared, or in component form g is 1 on y squared, 1, 0, 0, 1. All right, and with determinant, well, the determinant of that, because remember it's 1 on y squared there, 1 on y squared there, the determinant of that is simply 1 on y to the 4. And that implies that the square root of the absolute value of the determinant g is 1 on y squared. Okay, so far so good. So the associated volume form now on H2, a hyperbolic space, or a local coordinate system within that, because I'm not covering the whole manifold, but part of it. So it could be the volume form under the metric g here. This metric is square root of the absolute value of the determinant g, and this wedge product here. Okay, which is, remember that was the formula from earlier, but our coordinate system here is xy, so we're going to have 1 on y squared dx wedge dy, and that's our volume form in this space, in local coordinates here. Yeah, so here's H2, here's our set S, and our local coordinates xy, H2, and our volume form is 1 on y squared dx wedge dy, or just this format here. Okay, for whatever metric we have. Now, step 1, we're going to parameterize this because we want to perform an integral of this. So we're going to have some function we're going to integrate. Get to shortly. So let's parameterize the region S in H2 using polar-like coordinates. Phi is a map from the open set U contained in R2 to S contained in H2, hyperbolic space, two-dimensional hyperbolic space, with phi r theta being r cos theta, r sine theta equals xy. Okay, so phi is a function of r and theta, and this is the polar rectangle. I'll get to that shortly, but in Euclidean coordinates, r cos theta, r sine theta equals xy. R is greater than 0, and theta belongs to the interval 0 to pi. Now this parameterization maps the region U contained in R2, or in other words, the polar rectangle. R belongs to the closed interval AB, and theta belongs to the closed interval alpha beta. And we're going to into the curved manifold S contained in H2. So step 2. Okay, so there's our parameterization. Step 2 is now the pullback. Now compute the pullback of the volume form under G, under the metric G, under the parameterization phi. So phi is our map. We're going to pull back against that. So the pullback under phi, that's phi upper asterisk of the volume form G, is the square root of the absolute value of the determinant of G in the original coordinates composed with the map phi times the determinant of the Jacobian dr wedge d theta. All right, now notice there's no absolute value signs here at the moment. Okay, there will be when we go to the integral, don't forget. All right, so here's our situation. So here's our hyperbolic space, two-dimensional hyperbolic space here, local coordinate system S here on H2, and our coordinates in this local system here, XY. Here's our polar rectangle, R and theta in R2, and a point P in U is mapped to a point 5 P under this map. So phi is a map from the open set U contained in R2 to S contained in H2, and at the point P, here's our cotangent space. That's the cotangent space to the manifold U at the point P, and the cotangent space to S at the point 5 P here. Okay, and phi star is the pullback of this volume form here to here. Okay, so the volume form on here, we will pull back to here to make our life integration, to make the task of integration of the content of this manifold easier by pulling back to Euclidean domain. All right, so step one, compute the determinant metric in terms of r theta. So we have G as metric is 1 on y squared this, and the determinant g is 1 on y to the 4. So we found all this earlier, if you remember, found all that earlier. Using x equals r cos theta, y equals r sine theta, we get in the new coordinates the absolute value of the determinant g composed of phi of r. Well, if you just see here, 1 on y squared, well, y is r sine theta. So we're going to have 1 on r sine theta to the power of 4, square root of the absolute value of the determinant g composed of phi of r theta. Is then just going to be square root of that, so it's 1 on r sine theta all squared. And the determinant of the Jacobian here, well, the Jacobian is partial x y of partial r theta, so it's this matrix here. If we take the partial of x with respect to r, we get cos theta. Partial of x with respect to theta, we get minus r sine theta. Partial of y with respect to r, we get sine theta. And the partial of y with respect to theta, we get r cos theta. And so the determinant of this, if you worked it out, cos theta times r cos theta minus sine theta times minus r sine theta. So you're going to have r times cos squared plus theta sine squared theta, which is 1. So you just get r. We seek the pullback of the volume form under the map phi. So we get the square root of the absolute value of the determinant g composed of phi of r theta. We get the determinant of the Jacobian under this map phi, dr wedge d theta in our new coordinates on u. All right, so the pullback volume form in r theta coordinates is a pullback of this, is this object here. Okay, well, we found this object, so that's that. This object is this one, and here's our new wedge product of our new basis 1 forms on the set u. So hence the pullback is this object here. Remember there's an r squared here, so one of them cancels out because there's an r here, so we get 1 on r sine squared theta, dr wedge d theta. Now step 3, integrate some scalar function, whatever it is, over the region H2, your energy density, whatever you want, general relativity, whatever the case is, then to compute the integral of f volume form under G over S contained in H2, the hyperbolic space, two-dimensional hyperbolic space. We evaluate the integral of S contained in H2 of F vol G by pulling it back to the Euclidean domain. So it becomes scalar F becomes F composed of phi, so that pulls the scalar function back to the set U. And then this determinant part, we have to pull that back to phi as well. Then we take the absolute value of the determinant of the Jacobian to make sure we have a positively oriented unit volume, dr wedge d theta. And then we can swap now to the specific integral by integrating from alpha to beta, a to b, f composed of phi of that object there. All right. So that's actually, at this point, that's what we've said, that's what your end result is. We can't go any further, we don't know what f is. Let's just say, for argument's sake, just to show you how, if I set f to 1 here, then we're just integrating a volume area and producing a unit of area. And I just want to show you, if we integrate this over the region given by these limits here, we're going to get an area. And I just want to show you how this hyperbolic area is different to our Euclidean area. Even though it's not really a part of this topic for this, I just thought I'd just show you anyway. Anyway, so if we now set f equals 1, the resultant integral is just the hyperbolic area of the region S contained in H2. All right, so the integral of S contained in H2 of the volume form is this, as we've seen earlier, which the explicit integral is a specific integral here, the iterative one here. If we evaluate all that, I won't go through all the steps and so on, but we just do the 1 on r part, so that's going to be log b minus log a for the 1 on r part, and gives us that. If we then integrate this 1 over sine squared theta between the limits alpha and beta, respect to theta, then we're going to have the integral a to b cosec squared theta d theta, which is just a standard integral. When you do that, the end result is log b on a times minus cot beta plus cot alpha. Okay, so it doesn't look like length times width, does it really? It's a very different sort of thing. You have a logarithmic part here and you have an angular part here. All right. So whereas in Euclidean space we'd have one length times another length. Well, that's not the case here. It's a different type of space. So key points here, the logarithmic term log b on a reflects a scaling factor introduced by the geometry of the hyperbolic plane. The trigonometric terms, these ones here, arise from the angular contribution to the boundaries of the region in the chosen parametrization. And while the integral computes a hyperbolic area, so to speak, it does not correspond directly to the intuitive notion of area in flat Euclidean geometry. All right, conclusion. Integration on curved Riemannian, semi-Riemannian manifolds generalizes classical integration to spaces with curvature. The volume form derived from the metric encapsulates the manifold's geometry. All right, that's a point to point out. The metric's role there is to encapsulate the geometry. In Euclidean space, all that's just one, but in curved spaces, it's not. All right, while the pullback enables computation by transforming the problem to a Euclidean domain, making life easier for us. This framework is essential in geometry and physics, appearing in applications such as calculating areas, volumes, and action integrals in general relativity. All right, so I can come back there. Very important. You can see that semi-Riemannian manifolds are of interest in relativity, where they generalize the inner product under the metric. But you can see that in the Riemannian and semi-Riemannian manifolds, we must consider the curvature of geometry, and that's encapsulated in the metric part. Okay, then the pullback of the whole lot helps us transfer the integration problem on the curved manifold to an equivalent one on Euclidean space, and makes our life much easier for us to calculate it. Right? The pullback preserves the integrand, taking it from the manifold to the Euclidean space, and brings it over there so that we can work in that simpler Euclidean space that we're all familiar with. Anyway, I hope the video was useful to you. I hope you found it informative. I hope you enjoyed it as well. And I shall see you in the next video. Thank you very much for watching. Please, if you will, push the like button and subscribe. I would greatly appreciate that. And I shall see you in the next video. Take care, everyone. Have a good day, and see you next time.